Good morning, welcome. This is Mr. Tan coming at you from my basement because we need to keep learning math, and I love teaching math, and I got some awesome helpers today. First, I've got Shayla behind me. You say hi, Shayla. And McCallie. My daughters are here to help. So, McCallie, you are the camera woman. So, today we're going to learn about initial value problems. As you can see, I have a chalkboard in my basement because our basement is cool. And so we're going to talk about it on the chalkboard. So, you should have a paper in your Google Classroom, a PDF that says Initial Value Problems, Introduction. And that's where I'm looking, where it says Notes at the top. So, towards the top, it says, an equation like dy dx equals y times natural log of x that contains a derivative is called a differential equation. So, that first blank, we're talking about a differential equation. Okay? The problem of finding a function y in terms of x when we are given its derivative and a particular point on the curve is called an initial value problem. Initial value problem. So the last few days I had you working on some indefinite integrals. And so today what we're going to do is take those indefinite integrals and make them more definite. And what that means is we're going to figure out what that plus c actually equals. So here's an example, and this is the next thing on your notes. Suppose we know that dy dx equals 2x plus 1. First, determine the set of functions that the original function belongs to. Is this enough information to determine a single original function? Why or why not? So I'm going to write that down. dy over dx equals 2x plus 1. So if we were in class, like I wish we were, I would ask you, what kinds of functions, when I take their derivative, give me 2x plus 1? So think about that a minute. Which kinds of functions, when I take their derivative, give me 2x plus 1? So, you might think, well, 2x, if I go backwards, I know that it'd have to be x squared plus, and for the 1, I'd have to have an x. So, x, and then we've learned the last few days, hopefully, that we need a plus c, because we don't know what that constant is. Because if it's plus 1 and I take that derivative, it's 0. If I had plus 5, that derivative is 0. So, we don't know. So we know that it's going to be some function of the form y equals x squared plus x plus c. Now, the next part of your note says, suppose we know that y of 2 equals 5. Can we find the original function now? What is it? Well, I'm going to have to bend down because our chalkboard is made for younger kids. So if I know that when I plug 2 in my function, y of 2 equals 5, then what I can do is plug that in and help figure out what the plus c is. So if I put 2 in for x, so this is like saying x is 2 and y is 5. And so if I put 2 in for x and 5 in for y, we could figure out what c is. And this is what makes this an initial value problem. So if I put 5 equals 2 squared plus 2 plus c, I get 5 equals 4 plus 2 plus c. So 4 plus 2 is 6 plus c, and that's going to give me 5. Well, to get c, I'm going to subtract 6 minus 6, and I get that c, I'm going to move over to this part of the board in case we need to move the camera, c equals -1. So what that tells us is this specific solution is y equals x squared plus x minus 1. And that's my solution to this initial value problem. So again, if we were in class, I would say, what questions do we have? And we would pause and you might have some questions. So if you have questions, make sure you send them to me either through Google Classroom or post them on Google Classroom. That's probably the best, because maybe if I don't see it right away, another student could help you answer that. And I know we also have our group chat, so don't be afraid to ask questions on your group chat as well. All right, let's keep going. I'm going to erase this. So we usually write these problems using a specific notation, and I didn't do a very good job of that in that first example. So I'm going to show you more of the notation in this next one. So another example, suppose that we know that dy dx equals sine of x. So dy over dx equals sine of x. Okay? So if I were to solve for the solution, it says I also know that when I plug in y of 0, my answer is 1. So when I put in 0 into this function, the answer is 1. So to write this out in a little bit more of acceptable math notation, what we're going to do, when we have dy dx, we're going to think about this algebraically. I'm going to move that dx to the other side. So I'm going to write this as, I'm going to times this side by dx, and I'm going to write this side times by dx. And if I times this side by dx, the dx's cancel, and I'm just left with dy equals sine of x dx. So now we've learned using our integral notation that this is the opposite of derivatives. So I'm going to write an integral sign in front of both of these. So the integral of dy is just going to be y, and really you could write plus c here, and then over here the integral of sine of x is, let's see, when I take the derivative of something to get sine, it would have to be, I know that the derivative of sine is cosine, I know the derivative of cosine is sine, or negative sign. So I have to counteract that negative sign. So actually I'm going to say it's negative cosine of x plus a constant. Shayla, stay back. Do you want to get in the video again? Do you want to make an appearance? Shayla wants to make an appearance in the video.
Shayla, come on in.
You can say hi. You want to say hi a minute? Math break. Shayla wants to say hi. Go ahead. You can say hi. 1 minute.
Go on, Shayla.
Oh, she's embarrassed. Never mind.
She's shy now.
Okay. All right, back to math. So, now, notice that these are both C. So usually, if we had two C's, we would say this is C1 and this is C2. So rather than doing that, if you really think about it, we could just move this C1 to this side. So it would be like C2 minus C1. But instead of doing all that, we just are going to say they differ by a constant. So rather than having C1 and C2, all I'm going to do is I'm going to say y equals negative cosine of x plus c. There's some constant that's different between these. Okay, so now back to our initial value up here. I know that when I plug in 0, the answer needs to be 1. So I'm going to say, okay, so again, if I think about this, x is 0, y is 1. So when I put 1 in for y and I solve for c, negative cosine of 0 plus c. Okay, got to know your unit circle. Cosine of 0, let's see. So cosine is my x, and so at 0 degrees, the x value is 1. So this is going to be 1 equals, you have the negative sign, so negative 1 plus c. And if I solve and get c alone, add 1, so my c is going to be 2. So the final solution, so I'm going to move over here. Hopefully we can see okay over on this side. Macallie, can you see? Okay? Okay. So we have y equals negative cosine of x plus 2. And that's the solution to this initial value problem. So again, if you have questions, don't be afraid to post them on Google Classroom or send me a message either way. So that's how we do an initial value problem. There's one more example for you to try. So you might want to pause the video for a second. Don't pause our video, but pause the video if you're watching. And then I will start going over that in 1 second. So start it up after you've tried that last one. All right. So hopefully you've tried the next example. You might have gotten stuck on the antiderivative with the e, but hopefully you could have done that first step. So the first step is always called separating the variables. So this is actually called a separable differential equation because we can separate the x's and the y's. So we can get the x's on one side and the y's on the other side. So when I have dy over dx equals e to the 2x just 2x. So what it's saying is when I take a derivative of some function, that derivative is e to the 2x. So I also know that when I plug in y equals 0, or y of 0, the answer is 10. Okay? So we need to figure out the original function. So dy equals, again, if I'm timesing both sides by dx here and dx here, oops, that made it look like a power, dx. So I'm going to have dy, because these cancel, equals e to the 2x dx. Okay, I'm going to integrate both sides. Integrate. So the antiderivative of dy is y. Again, we could say plus c. However, we don't need that because we're going to put it on the other side. Equals. So that what when I take its derivative is e to the 2x? Well, I need to put a half out front because I'm going to counteract that 2x and then I'm going to say e to the 2x. Because you probably remember me saying the derivative of e to the blah is e to the blah times the derivative of blah. Well, I need to counteract the derivative of 2x, which is 2. That's why I need the half out front. You might need to replay that explanation a few times if you're not sure what I just said. Okay, plus c. So with a video, it's kind of cool because you could pause it and replay it, and you could just keep hearing Mr. Tan explain the same thing over and over and over. Wow, that's cool. Okay, so now I know that when I plug in 0, the answer is 10. So I know that 10 is my y equals 1/2 e to the 2 times 0 plus c. And if we keep going here, 10 equals 1/2 e to the 2 times 0. So 2 times 0 is 0. So e to the 0. But I know e to the 0, anything to the 0 power is 1. So 10 equals 1/2 plus c. Okay? So actually c here, I'm going to put the c. C is going to be 9.5 or 9.5 because if I subtract the half. So my final answer in this example is y equals 1/2 e to the 2x plus 9.5. Okay, so that's the third example on that first page. On the back side, you have several problems that are initial value problems to practice. So if you look at the handout I posted on Google Classroom, you can continue on to the back side, and there are 6 problems. So that's our assignment today, and probably tomorrow too. I don't think I'm going to be posting a video tomorrow, but just know that I miss everyone. I wish we were at school. I don't have answers as far as how long this will go or when we'll get back or when your test will be, but I know that all of you want to keep doing your best to learn calculus, so I'm going to keep teaching it the best I can. Take care.